We're back at the end of part one. We were just doing this convolution, and we've done some integration by parts here. So let's go ahead and keep going. We've already done the integral of sine of x dx, and we know that that's negative cosine of x plus a constant. But since we have a definite integral, we won't need to plus the constant. So this first piece will be t times cosine of t, negative cosine of t, that is, minus negative cosine of 0. Okay, so that's this first piece. And let's look at this next piece. And I'm gonna circle this minus sign so we don't lose him. So minus, okay, we're gonna put a t in here, so we'll get t times negative cosine of t minus, put a 0 in, we'll get 0 when you put a 0 in for the x. Okay, and then I'm going to wait and distribute that negative through again one more time a little later, but since I still have him here, I'm going to leave him be. So the integral of cosine of x is sine of x evaluated from 0 to t. All right, let's see what we've got now. So we've got negative t cosine of t minus a negative is plus 1 times the t is plus t minus a negative is plus t cosine of t, 0, 0. And now I'm going to distribute the negative over this as well. So we'll get plus sine of t minus sine of 0, but sine of 0 is 0. And minus t cosine of t plus t cosine of t makes 0. So the convolution of sine of t and t works out to be t plus sine of t. Okay. All right. So that was interesting. One thing that I will mention is if you'd wanted to, we could have used our table of Laplace integrals Laplace transform / integrals. And if we'd wanted to, we could have saved ourselves some integration by parts and just referenced table number 38, where we've got integral of u sine of u to u is sine of u minus u cosine of u plus a constant. We'd change that to a definite integral integrating from 0 to t, and then we wouldn't need the constant. But you would see that exact same thing right here. Okay, so feel free either to practice up on your integration by parts or use your integral table. But if you use the integral table, tell me that you used the table and which line you used so I can identify if you've made any silly mistakes. All right, so let's go ahead and use techniques that we've done before to find the inverse Laplace transform of this guy right here. Well, let's break him down into his partial fractions. And I note that I've got a repeated linear factor. So we've got a over s plus b over s squared plus, and then I've got a quadratic factor. And since this guy was already a proper fraction, each of these guys is going to be proper fractions. So since this is quadratic factor in the bottom, this will have to be a linear factor in the top. Okay, so if we do our partial fractions work, getting a common denominator here, and then if the denominators are the same on an equation, then the numerators must be equal. So we would get 1 equals a times s squared plus 1 plus b times s squared plus 1 plus cs plus d times s squared. Okay, and I'm going to rewrite this as 0s cubed plus 0s squared plus 0s plus 1. Oop, I gave myself a little too much space there. Equals, and then let's write this out. So we've got as cubed plus as plus bs squared plus b plus cs cubed plus ds squared. Now this would set up a linear system, but there's good news. If we're careful, we don't have to even rely on a calculator. Because this is an equation here, the coefficient of the s cubed on one side has to equal the coefficient of the x cubed on the other side. So 0 has to equal a plus c because of the s cubed coefficient being 0. And maybe I'll write s cubed over here. S squared, well, the coefficient of s squared on the left-hand side is also 0. And what do we have for s squared on the right-hand side? We have b plus d. Okay. And similarly, the coefficient of the s on the left-hand side is 0. So 0 has to equal, oh, check that out, a. Oh, that's nice. So if a is 0, then that forces c to have to equal 0. And lastly, the constant term, b has to equal, so we've taken care of him, b has to equal 1. And if b is 1, then d has to equal -1. So our partial fraction decomposition then would be 1 over s squared times s squared plus 1 is equal to, let's see, we got a b is 1. So we got 1 over s squared plus c is 0 minus 1. I'm going to bring the minus down here, so minus 1 over s squared plus 1. And those are guys that we recognize from our Laplace transform. 1 over s squared we recognize as the inverse Laplace transform. If we do that, we get t. And of course, s squared plus 1 we recognize as the sine. So if we do the inverse Laplace transform of all of this, we will get t minus sine of t. All right. Oh, I made a mistake. Oh, good thing wait, let me double check. Aha. I just noticed I made a mistake here. When I was doing my integration by parts, I did uv minus the integral of v du, and I forgot the negative sign here, so let's fix that. So let's fix that negative, and therefore that makes this be a positive, which makes, when I distribute that negative over that, that makes this become a negative here and a positive there. So that should have been a negative sine of t. Okay, Professor Pedrero is human too. He makes mistakes. So, all right. How did I catch that? Well, I know the punchline. This thing and this thing look amazingly alike. And why is that? Well, let's take a look at 1 over s squared times s squared plus 1. I could rewrite that as 1 over s squared times 1 over s squared plus 1. And here's the magic. So if I do the inverse Laplace transform of this, sure, get that inverse symbol in there. Okay. Hey, that's going to be whatever this guy is, convolute whatever this guy's function is. And we know that the inverse Laplace transform for 1 over s squared is t, and the inverse Laplace transform for 1 over s squared plus 1 is sine of t. And what did I just have you do earlier? I had you find the convolution of sine of t and t, or which is the same as t convolute sine of t. So you'll notice that this guy and this guy are equal by design, and that's why we use the convolution theorem, is we can take and solve this problem, if he's nice, in a different way instead of having to do partial fractions. So let me stop there and we'll pick up with another example at the start of the next video.